Can we do some whiteboarding, maybe, to describe what's going on with the...
So who are you?
I'm Charles from Channel 9. We are here with George and Satnam, who are working on a very interesting project called the Concurrency Runtime. Many of you are familiar with concurrency problems on Windows and any other platform. It's just a hard problem.
So these are the guys who are building the software
guys that are actually figuring out
for the
how
new
to,
multi-core.
Sure, that's one way to look at it. True.
Okay.
So what are you building? What's going? First of all, tell us about yourselves. Let's step back. I'm excited about CCR, but let's. So who are you?
I'm George Chrysanthakopoulos. I'm a developer here in Picked Up Group, and we've been at this for a couple of years.
Okay.
And I think we're getting somewhere.
Fantastic.
Something useful, something practical, something you can use immediately today. So.
Okay.
Now, does your technology ship in any product, or?
Absolutely not.
Okay.
But that's what we're trying to make happen.
Okay.
Yeah.
Hi, I'm Satnam. I'm also a developer on this project. I joined relatively recently, just last year. Most of my background's in hardware and doing concurrency in hardware. So I'm trying to bring some insights from the hardware world to the software world to try and make current parallel programming a little bit easier than it is right now.
Sure. Now let me just ask this again. Why is it so hard? I mean, we're talking about managing multiple threads. I mean, kernel guys do it all the time, right? But it's hard because you have to manage your locks correctly. You have issues with reentrancy. Shared memory in general is a complex problem. So, what are you guys doing to make it easier? So, what is the common concurrency runtime?
Well, so one of the problems with a concurrency is that when you've got two programs running at the same time and you want to debug it, you're kind of forced to think of all possible interleavings of these two programs, and that's incredibly difficult. When you've got just a sequential program, you go into a debugger and you step through it line by line by line, and you can freeze it, and you know that this statement runs and then the next statement runs. Those assumptions are totally false for concurrent programs. So all kinds of variables get accidentally modified and mangled, and it's very hard to reproduce the errors. If you've got a buggy sequential program, probably every time you run it, you might see the same errors.
Precisely.
With a concurrent system, it's non-deterministic. Different things are going to happen every time you run it. These are some of the reasons why concurrent programming is pretty challenging.
Absolutely. It's an excellent point.
So the other thing, as far as, we started trying to do something with distribution, which meant that we tried to use resources outside some local scope.
Okay.
And invariably when that happens, you find yourself having to deal with partial failure, which means in order to do one thing, I have to send 5 messages or call 5 APIs, and in any order or anywhere they could fail. Now forget about the fact that they're concurrent. The fact that you're distributed automatically means that they're independent of you.
Yeah.
So the way we approached this actually was, forget about concurrency for a second.
Sure.
What you really need to be concerning yourself with is coordination. And once you start tackling coordination, you're going to enable concurrency. Because as Satnam said, the primary fear people have when they write concurrent programs is they are scared in coordinating those possible interleavings. So this had nothing really to do with concurrency. What this really had to do is about enabling you to write pieces of software that are communicating on some interaction points, doing complex stuff. That if I tried to use Win32, I would write ad hoc code of hundreds of lines every single time in order to do some very basic stuff. So all we did is we codified it. We created some generalized architecture where you can arbitrate, where you can coordinate. Okay. Now people are not afraid anymore to say, go to database, go to this, and go to that. In any order, receive the messages. Or, if any of them fails, do that. All this I just described is 3 lines of code. So now you're going to start doing things concurrently versus go to database, wait. Got database or failure result. Now go to logger. Got it. Now go to the next thing. I made it sequential for no real reason other than I'm scared a lot.
To make it asynchronous.
Correct. Asynchronous.
Well, but the beautiful thing about asynchrony, obviously, is that you don't have to mess with your UI. Doesn't freeze. I mean, I still see applications.
Exactly.
Responsiveness is important because I still see applications today, and it doesn't matter who wrote them. That's not the point. I see plenty of applications today where their asynchronous code they're not using asynchronous code either correctly or they're not using it for the exact reasons you're talking about. What you're saying is CCR makes me less afraid to write a complex asynchronous application because
they give you coordination.
you give me coordination.
So it's really about responsiveness.
So how do you
believe it or
let's talk
not?
about how do you pull that off? And so is this sort of like, I mean, what is the concurrency runtime again?
So it's
What-
just a
what's
library.
going on?
It's really just a library.
Okay.
It's just a library with a lot of stupid pet tricks when it comes to using operator
Smart
overloaded.
pet tricks.
Okay. Tricks that we're doing to make the code concise, as type safe at compile time as possible, efficient, and essentially, as a library, once again, codify some common patterns in some efficient way, and take care of distributing work on each processor on your system.
Now,
But it's a library. It's a library. I mean,
understood. I mean, it's the runtime, right? I mean, the point is, though, you're saying that with your runtime, I can write asynchronous code that's reliable because I can tell you when to run it. Or I mean, let's talk about that for a second.
Right, right.
It still has to be there still has to be multiple threads running.
Absolutely.
So, and there still needs to be a reliable way to get information from those threads back to my main UI thread. All that kind of stuff,
Absolutely.
which is a big problem. So, what are you guys doing to make that easier for me? Can we see an example,
Sure,
or
sure.
I mean, or draw a picture of what's really going on?
I can just start by saying the way we usually think about this is in interaction diagrams, which is how networking people say it. And
Fantastic.
the reason I do this is because it's actually a fairly intuitive way to show some application. So I'm just going to say here I have some main process, right?
Okay.
And this guy, what he wants to do is maybe read a file, right? But there's also this little UI thread over here, and these lines, think of as an independent process.
Okay.
And if that's simple, think of it as an independent thread. It doesn't really matter. For us, threads are more like logical things. They're not the actual OS thread.
Sure.
But there's this logical flow, right?
Okay.
So you want to read this file, but you also want to be responsive to something coming from the UI. So you send this request, and potentially sometime later, you're going to get done from the file
Sure.
system. Now, sometime in here, somebody said, shut down. How often do we see things say shut down and everything?
Yeah.
Now, actually, you really do have to wait for this anyway to happen. The question is, can you bring up a little dialog box saying, hey, I'm in the process of doing something. Can you have a little progress bar? What I'm trying to describe is, in order to deal with this problem using the CCR, you basically use these little interaction points that we call ports. And then you use our primitives to remain responsive and coordinate with messages. So it's really traditional applications that we're talking about, doing some file I.O., doing some network I.O. that is asynchronous, potentially takes a long time.
Sure.
So instead of blocking a thread, which is nothing inherently wrong with blocking a thread, except that people are scared to have millions of thousands of, millions of threads, because today tends to be inexpensive.
Sure.
But even if you did have lightweight threads, you still want to coordinate between them.
Exactly.
Because even if I had lots of these, and there were indeed threads, the CCR has nothing to do with the synchrony per se, because this could be done on threads. It has to do with coordination.
Okay.
So, talking about concrete code here, you could do something like this. You could say, hey, I'm going to show you activate. This is a little, library call, and I have some, file result. This is a port. And I want to execute some code, done with file. Using the OR operator overload, you can now combine this what are we saying here? We're saying run this code when something happens on this port.
Okay.
Or you can say, well, one of the things that could happen, of course, is that it could fail. So you say OR with failure. Right?
Okay.
Or you could say, and I'll explain what this bang is, UI with, handle button.
So we should get rid of this over here.
Yeah.
Yeah.
Now I can put a parenthesis and thing down here. So here's what we've done. We said, at any given time, I don't know when, I'm going to get some success from the file read operation, or some failure. But while this is happening, I might be getting UI messages.
Okay.
So I make this a permanent receiver. These guys are one time. Once this fires, this whole thing turns down.
Sure. Good.
This is kind of convenient, right? Because
Very.
how many times do we have wait for multiple? We always forget to put a little branch in there, which is the cancel branch or the UI branch or whatever, and we just lock up. This will take care of tearing down this whole thing. So even a second message by accident gets sent, if you have things other than files where they might send multiple messages, you don't have to worry about it. We will clean up this little pesky UI that is like a progress bar, or it does drawing. So this is an example, just using this operator. We created some arbitration context in our world, and we're coordinating on some things and letting you do some application logic. Now, it gets interesting when you start doing the stuff that we call joins. And what I would like to stress is that we didn't really come up with these primitives. We came with a generalized architecture of nesting these primitives, which I don't think many people have done, but these primitives have been around for a very long time.
Okay.
Select, join, they've been in NT and in other languages for a very long time. But as a library, with a generalized architecture to combine them together and nest them, we think this is something new. So another example I would like to show, which is very useful, and it's again useful in the literature, is what we call joins. So I want to join on message A, message B, that will come from port A, port B, dot, with some code here. And by the way, because this is also C# 2.0, I would like to point out that this is really concise, because you can inline put the code. So look, you can say message A, message B, B, and here I have some application logic. It basically says, when you get a message on this port, think of the port as a queue. It's nothing more. It's just a little queue.
All right.
It's just a queue. So you get something on here, and you get something on here. Any order. When you get both of them, run this. Very useful.
Very useful.
What's even
A key feature about that is that the acquisition of values in A and B ports is atomic. It happens in one indivisible swoop, and that's very tricky to try and program otherwise. So that's a very powerful feature of these join patterns that Giorgio is describing here.
Fantastic.
So it's an atomic.
Very cool.
People either see both disappearing, or they don't see anything. What's even better is that if there is contention, and somebody, without you knowing, I'm just putting it here just to show you that there's contention. Maybe there's two of us that are listening for message A, and maybe I'm listening for message C, but I don't know about you, right? What is the problem with deadlocks? Is we write some code that takes lock A and lock B, and then 30,000 lines deep in our code, we realize we need to take A, but we also have this other completely unknown thing called C. Well, I forgot, so I take C first, then A. We're now contending on some resource without knowing. There's this implicit coupling. Joins have this magical property that the order you mention them is completely irrelevant. What they will try to do in a two-phase operation is they basically say, is there something on A? Is there something on C? Yeah, okay, well, let's attempt to get both of them. If you don't, you put A back. Think of having a locking scheme where you take lock A and you take lock B, and you're like, shit, I deadlocked. And you're like, okay, like
That's
it never
a technical
happened.
term, by the way.
Sorry.
Right, we're adults here.
Right. And you put it back. Nobody knows. That's really powerful. It has, limitations and pitfalls, but we really use this a lot for certain things.
Fantastic.
Now, joins is one thing, but I would like to show once again that here, while you're doing the join, look partial failure handling. This is combinatorial, right? You understand that I could get A but not get this, I could get this and not this, or I could get both of them. As the number of messages I'm expecting, the partial failure cases are huge.
Sure.
So what you could do here with us, in the CCR, is you could actually use the same port twice. It doesn't matter, but it's typed to two different messages. You can actually have a single port that takes instant strings. But you can do things like this. You can say, assume this is the same port here, A. And if you get a failure, it's going to be sent as a different message. It's going to be a message, message F, I'm going to call it. So you're going to say with delegate message F some code. So here's what I'm saying. If you get success, you're going to get message A on port A. If you get success from B, you're going to get type message B, but also on port A. Think of little independent sub-queues.
Okay.
If either A or B fail for some unknown reason, they're going to send the same message, failed.
Exactly.
This one thing is all you need to cancel this whole thing from ever running.
Or handle it inside the code.
Yes, here you
You
handle
don't
it.
have to just fail.
Right, you handle it. That's what I mean by failure.
Understood.
Right.
Cool.
I don't have to say, I got A, but I didn't get B, or I got B and I didn't get A. What we do is we post everything back.
Cool.
It's like it never happened. In here, you can go in the queues, clean them up, do whatever you want. But instead of doing wait for multiple, go to some independent queue, look at it and do some variable comparison. This OR basically means they're exclusive of each other. If failure happens at any time, forget about all this and all the combination.
Wow. So if you don't use this the OR case here, and we get a failure in one of the queues, say message B,
This
you're still
doesn't
going to
fire.
fail.
Well, no, this doesn't fire.
Sure, this only runs in success.
Exactly.
So, but the point is, if it's a bad exception, then it's the CLR will handle it, like out of memory exception or something. The CLR will just shut down.
Right. This doesn't run. This doesn't
Perfect.
run.
Of
And
course.
actually, you will even get garbage collected. Because if you have nothing else keeping this alive, this might get garbage collected. Now, look, partial failure handling, while you make this, you see, it's all about unifying things to the degree possible to a common set of primitives.
Sure.
I do not believe in scale invariance. I really don't. I don't believe there's really one set of primitives I can use everywhere. But if we can get away with it, why do we have events? Why do we have begin and end task?
Yeah.
Can you imagine in the CLR today, you do begin file, read, do another begin file, read. How can I couple them and coordinate in this way? I can't. I have to have two completely independent handlers run in arbitrary thread context and check each other's thread memory somehow to need the other guy failed.
Precisely.
And then I have events. What the hell are events? Events are this thing that you never know the execution semantics. Sometimes it's reentrant, sometimes it's your own thread, sometimes it's some random CLR thread, and you just don't know what to do. This is consistent. Eventing, async, because you understand, arbitrarily, at the bottom, it's really just sending messages and making it accessible to people.
Absolutely.
So that's all we're trying to do, is just limit the number of primitives and start getting a hold of it.
And these are dynamically constructed programs, so they actually live in the heap, and that's why they can be torn down, reassembled, and reconfigured. And that makes them quite different from kind of joins you've had in other programming languages, like Kajou, Camel, and C Omega, where joins appear as declarations, as syntactic things to your language. Because we've got a library, you call a library to dynamically construct your CCR join-based interleave program.
Fantastic.
This is actually a very key point. It's very powerful. Think of this. You start your program, and you go to a file directory. You have no freaking idea how many files are going to be there. You enumerate it, and there's 1,000 files. The CCR is about commands. It's imperative. You can actually issue a join that says, if you receive literally 1,000 results back, do this. Because it's a command, it's dynamic. I can actually put a little counter in there, and then issue it whenever I feel like it. Imagine now recreating a class that has a declaration time 1,000 receives for a message. It becomes very tedious to code that way.
And this lets you do things like scatter-gather operations. You can scatter 1,000 things, they happen in parallel, and then you just join on the 1,000, and when they're ready, you've synchronized, and you can do the next thing.
Now, what about the performance implications of this joining, this dynamic code generation dynamic? Is what you're talking about right now. There has to be. So what's the cost?
Right.
That's my question.
Right. So, if you have a language and you have a small number of joins, you can do a lot of things at compile time, which some languages do, and create this state machine, basically state diagram, and kind of tune your join logic. Because it turns out some permutations will never be taken. The way we did this, however, is that I believe it's a very incremental gain or loss using some interlocks, which is what I use underneath. There is some counters. There is no global locks. We don't lock across 5 ports. We just do atomic test operations. So it will be slower. For certainly be slower. I would guess that for a dynamic join of a join of many members, it starts evening out. If you have a very small number, which a lot of these languages deal with, like get state and do this, Yeah, they'll probably be faster. They can recognize you don't need to run it async and stuff like that. But in reality, I find myself very rarely having to do trivial things. Because if it was trivial to begin with, then a couple of locks and threading would have worked just fine.
Sure.
So it is costly today because we're running on an OS where threading and context switching is in the order of hundreds of nanoseconds. This stuff, to give you an idea, to run a very basic little UI app we have, we can generate up to 1 million possibly concurrent items. Because think about it, everything, even a UI, can be done concurrently. Any message you send. We basically become alive, do some more I/O, and we evaporate. And we're heap, as he said, we're completely heap-based. There is no stacks. We wake up on just one thread per CPU. We have to use threads. That's what the OS gives us. That's it. We generate 15 million concurrent items running one of our, basic tests, and they were all load balanced at 99% utilization across 4 CPUs. Now look, this is not magic. If you use the thread pool and you did your own queue user work item and stuff like that, you could get load balancing like that. But there are no synchronization and coordination in thread pool. Nothing. All you have to revert back to is wait for all and wait for multiple. Which, by the way, if you call it from arbitrary thread context, you will deadlock the thread pool. Because you will run out of threads.
And
Fantastic.
in addition to just performance, I think another issue is just correctness, being able to actually write correct programs that you can understand and maintain. I think it's probably better to have a slower program that gives you the right answer than a program which quickly gives you the wrong answer.
It also lets normal humans play in this world, doesn't it? This is going to let normal business programmers do this kind of programming.
We're hoping. I mean, that's really what we're hoping by making it accessible as a library.
Sure.
A lot of people are really trying to give you a new language with formal semantics, and which is all goodness in some sense. But you really have to realize that when you design a language, you're going to get 90% of the things wrong, and you're going to get 10% right. So why don't you start with a language that people have gotten a lot right to at least a very broad domain of users, and add as a library something that can start tweaking and give you iterative feedback.
Sure.
The thing to understand about the CCR, didn't wake up one day and said, hey, shit, I'm sorry again, join, choice, interleave, this and this. It didn't happen this way. People came in the office and said, we would like not to do this manually. Could you codify it? And it was iterative. You need users. You need an application.
Absolutely.
When you design a language, you have to have this incredible intuition to get it right. And you never do. Unless you're, I don't know, brilliant or whatever. No, but, I mean, come on, even C#, it didn't start from scratch. It's very Java-like in many ways.
Sure.
You see what I'm saying?
Precisely, everything builds up
It's
on
iterative.
So you guys are actually running on top of the CLR,
Yes,
which
we
is
are.
a beautiful thing, which actually gives it back to what Robert was talking about. So VB people can use this.
Yes,
It doesn't matter
yes.
what language, what's
Yeah,
We've got
syntax
an
you like.
example of people using CCR in the F# programming language. It's a wildly different functional language based on OCaml and ML. And because the library it works on the CLR, you can interrupt with it from lots of other languages as long as they are CLR languages.
Are those the researchers in Cambridge doing
Yes.
it?
Yeah.
We interviewed those guys.
Yeah, those guys are smart.
Yeah, very interesting. They like functional programming.
Yeah, they do. But actually, to be honest with you, before I saw F#, I wasn't very big on functional programming. I think it's kind of hard to parse, even if it's extremely concise. And I like this imperative nature, but F# is kind of like the best. I'm going to give it a small, it's like the best of both worlds. It has Don Syme, as a matter of fact. Satnam goes to him and says, I would like to write some CCR programs, but it's kind of nasty because I have to do this kind of jumps and hoops and whatever. And very quickly, he gave us a very concise way of doing handlers. But it's still functional. You can still do other stuff and still use the CCR.
I'm opposite from Giorgio. I think functional programming is absolutely beautiful, and this imperative stuff just makes my head hurt.
Yeah.
So at least now with F#, I think it's kind of a way where people can choose which direction to go.
What are the few things that they need to do to get started? What do they need to know?
So at the CCR level, which we're talking, they just need this library, and the paper that Satnam put together to give you an idea, and we have some samples, and you're often going. I mean, you can wrap WinForms, you can wrap file I/O. You can the way we built all this, by the way, there is no global scheduler, so you want STA affinity, which is huge. For example, I want to wrap UI and still use the CCR, but I want to be guaranteed that I will always get called in the same context. You can do this in the CCR. You can associate a dispatcher context pair with. This is extremely powerful.
Excellent.
It basically makes legacy interop with Windows feasible versus completely infeasible. A language that has no thread affinity concerns is dead end for Windows, unfortunately.
Sure.
But we let you do that. We let you interface with things that have affinity, but your code doesn't change.
Fantastic.
To you, it looks like I'm doing CCR things, but of course, it's stuck on one thread. Once the lower level API is munged or fixed, all of a sudden I run as concurrent as physically possible in this machine. But my code does not change.
Fantastic.
Yeah.
So are
it
you
was-
doing any work with attribution? So you can attribute methods to set and then pass in information as opposed to actually having to put your code
Imperative.
in line. Yeah.
Right. So one thing about the imperative thing, as I said, it's dynamic. If you do
Understood.
declarative stuff,
Yeah.
you can very easily do this with a CCR. For example, you can say, here's my... We actually do this in our distributed model.
Okay.
You annotate the port and we wire it.
Cool.
We wire it with the methods. But remember, that's very inflexible in some ways, but it's concise.
Uh-huh.
And remember, if you start with an imperative thing in C#, you always can make it declarative. If you start with a declarative thing, you have some very serious runtime considerations. So we try to get this thing, make these things very simple, very unified. And if you want to put a different syntactic front end, go ahead. By the way, this is just syntactic sugar. If you look at our wiki, which is also on channel 9, you will see that in the end, underneath,
Yeah.
all of this disappears, all of it. And it becomes this little formulation of data structures that get posted to a dispatcher. So this whole join I just gave you
Yeah.
is nothing more than this. New post, new tuple, some port, new join, plus the parameters I gave you. Everything in the CCR becomes a send. Receive is a privileged instruction in the CCR. It means that for you to receive, you send something. Everything, the join, the choice I gave you, spawn, we have this sugar, syntactic sugar we call it. Spawn some code, H. You can actually do it like that. This underneath translates to the dispatcher, post, new task, parametric on H. Everything is the same thing, derives from iTask. Even the arbiters, the way the joins go on those ports to listen for your messages happens asynchronously.
Fantastic.
So there's an extremely small number of primitives, and the ports are super simple. We didn't try to put any processing complex logic in the ports. It's all in the arbiters. We can do stuff like, you can do XML parsing and shredding using the CCR by running an arbiter that does value comparison on some XML queue names. Or you can use it using the types. This is the beauty of a generalized architecture. V1 of this wasn't generalized.
Sure.
V2 is generalized. But at the same time, it's very lightweight. So you can do your own arbitration. For example, in the CCR, you can do something like this. P with, 5, and then the handler. What this means is, if the value is greater or equal than 5, for example, so P with equal, greater, whatever, 5, run this. You're going to do value comparisons.
Fantastic.
You can say, if it's equal to string, foo, run this handler. Otherwise, it's like it never happened. So I didn't try to cram the logic in little port variants. It's just something you decide. I'm going to give you some arbiters to begin with. Then you extend it without screwing up the underlying logic.
Now, is this version dependent in terms of the CLR? Are you guys required to 2.0?
We are hardcore dependent on 2.0 because it has this wonderful thing that's called generics. Int, string, port, P, my port, new. This is typed. If you try to do on this port called PM, post 5,5.5, this will bar for compile time. So we like generics. The other thing it does, this is a neat trick again. You know how I told you when you do this with thing and you give me this H code?
Yes.
I actually, at compile time, we look at the parameters of H and extract the sub-channel of this to verify that this port can indeed send messages that this code can receive. So you can't do things like associate a piece of code that receives floats with a port that only gets strings. This is actually, generics don't just give you that. I mean, it's just some stuff we had to do to make it safe for you because we're not a language.
And we do anonymous delegates as well, which is
Anonymous delegates is huge. Here's a huge problem about message passing. Oh, and iterators. We haven't even captured iterators. Anyway, so anonymous delegates are huge because of the following. Let's say this was a port and you post ints. So this guy is going to wake up in some context, right? And I'm going to activate it. activate is the posting to the dispatcher I just said. It basically says just wire this continuation with this code. So I have this piece of code, and it's going to wake up and then maybe do console write line I plus, y. Now, where is y? I didn't declare it in this routine. Anonymous delegates do capture for you. So if up here, edit int y equals 5, I don't have to explicitly pass it through messaging. Messaging is a nightmare. But first to admit when it comes to passing certain state around. Context has to be explicitly passed. C# makes this easy because it does this automatic capture for you. So now I can just mention it. This is very elegant because I have all my logic in one routine and have this thing that runs in arbitrary thread context, but I can still use its variables.
Fantastic.
It's of course dangerous if you have multiple of these guys trying to use the same variable and all that, but I actually embrace some of the dangers in C# because it's just one of the prices we pay, because the path of least resistance actually tends to be value variables and stuff like that. Everything else is important.
Well, you could catch conceivably that problem at compile time, right?
With some analysis.
Sure.
Right.
So
But-
static analysis tools would be run and quickly tell
Exactly.
you, hey, you're using Y in multiple contexts, or etc.
Right. And the CCR makes it very visible, by the way. We only have one primitive, the port. You don't have sometime a semaphore and an event or a thread pool thing or a overlap structure. It's one thing. So you could actually tell that this is running in a different context. But whenever somebody says static analysis, I wave my hands and proceed to something else. So the iterative stuff I wanted to tell you is something that we find extremely, extremely powerful. So continuation passing style, which is what this leads you down, is kind of like the following. I have some handler called phase 0, and he gets some message A. And then this guy needs to talk to some new service, B, and send some new message that's parametric on A. And then asynchronously needs to activate phase 1, right? So now you need to say, message P response with phase 1. So what am I doing? I'm playing tag here. I wake up in phase 0 because I need this message. I send a new message, but now I can't do anything else unless phase 1 runs. So it's basically this state machine that is very simple. It's just a sequence of things. In threading, I would have done something like this. I would have said, P service A, post something. Then on that message, it has some response port, wait. Right? And then I get some result. Now below, I do the second step of my process. Service B, post message parametric on R. Again, message B, P response, wait. Let's just wait. I get R prime, blah, blah, blah. It's all in one place. I don't need to nest continuations and asynchronous things. Well, what did we do? We actually used iterators in C# as a scheduling mechanism. So what you can do with us is the following. Anywhere you could do activate, the algebra we have works out, you can do yield. So you can say yield return message P response with, here's a little stub, I'm just going to say del here, right? It has some result R. In line, in the stack here, I'm going to declare the result, R0, and it's set to null to begin with, right? In here, I'm going to export it outside. Let's erase this. So here what I'm going to do is I'm going to say R0 equals R. All right? Now this code here, look, step 2 of the computation. Service B, post a new message that is going to now use R0. Now the trippy part about all this is that this only runs after this runs in some arbitrary context. When you yield, you didn't block a thread. So I can go from stage to stage to stage by basically saying, I now need to yield. Our scheduler says, oh, you're just a work item. I'm just going to let you go. When the message comes in, you magically reappear here. Because we go to the iterator and say, move next. But what are you moving? You're moving code points. It's really like doing thread instruction level capture and rehydration, capturing, all the context.
Excellent.
The registers, blah, blah, blah. In our case, what are the registers? They're heap captured stack variables.
if we had baked these features into programming language and we wanted to have this continuation passing scheme work for us, we'd have to do a sophisticated transformation called a continuation passing style transform. And it's very hard to do. With yield return, we use these clue style iterators to trick the C# compiler to do the CPS transform for us. So that's us write code which kind of looks as if it's blocking style code without actually doing real blocking of threads.
Outstanding.
So you have state
Very,
1,
very
state 0.
cool.
All in one routine. No need for call this handler, which this handler then queues this other handler, and it's spaghetti. And you talked about kernel developers. I was in NT, writing drivers a long time ago.
Yeah.
We actually get that wrong all the time.
Of course.
But absolutely, it's a very astute observation that they run in arbitrary context. They use with things called DPC, deferred procedure calls. What are those? They're very similar to our work items, except that we are in C# and we have all these little tricks to make it now easy. Plus, you can't corrupt memory, which helps.
Yeah.
But the driver writers are really used to this thing, and they get it wrong all the time.
Sure.
But at least they have some semantics. Where the rest of us doing multi-threading, we have no semantics. Some people use shared memory, some people use waitable queues, some people use completion ports. Where in driver mode you have to use device objects and herbs and all that.
Absolutely.
So we're very
Whole
similar
different
to
world.
that.
Which may change.
Yeah.
Very cool. Well, it's so excellent. So now, can we talk about time frames, Dr. Skoll?
I don't know. That's up to them.
So you right now you're still in. You're not code complete, obviously.
No, actually, the CCR has been dog-footed and used and pretty stable for quite some time.
Okay.
But what we're going to try to do is release an SDK of just the CCR, which is it's pretty well baked.
Okay.
And again, iterate on it. It's an SDK. If we find some issues with it or some good syntactic whatever, we'll add it. But we think it's imminent where we can release an SDK.
Now, what's your feedback been from internal developers? That have been using it? Are they psyched?
So a lot of people have done that had to solve the same problem using threading. And all I'm trying to say is that if you just want to call a routine and do some trivial computation, don't use ports and don't use messages. That's why I'm in C#. Use a function call. But the guys that try to do the same exact complexity of programs, not using the CCR, and then they use the CCR, because inevitably everybody does this. You offer this to them and they're like, I'm not really familiar, I'm just going to do it with threads. And they come back to you and they're like, crap, I can't do this. It's too much stuff, or I have to keep maintaining it. There's all race conditions. They will come back and use this and be very happy. Now, we don't have oodles of developers, but we have, I would say, 5, 6 people have been programming on this for a while.
Well, also theoretically, this could be used at a lower level in the CLR, for example. It could be
hidden from.
So when actually you think you're using threads,
Yes.
certain contexts, you're actually using ports, or using your model, which to me, this is a great model. It's understandable. Whereas complex threading, and the whole, the fact that we have to use threads in the first place is a whole different argument.
Right.
And that may change someday.
Right.
That's, maybe 15 years, maybe.
For a long time, we've
No
known how
threads.
to write programs, assuming a threading model and a blocking model for the programmer, but then behind the scenes transfer it into this continuation passing style to get very efficient execution programs. So you have languages like Concurrent ML, which do that. In Concurrent ML, people write blocking style code, but compile it under hood, compiles them to continuations, and you can have millions of these things going, because these things are totally stackless. They do some calculation, and then there's a go-to to somewhere else, and it's handed all the information it needs to do its job.
Right. So as we get closer to, say, processors with, say, 32 cores, this type of construct is going to be very, very helpful for developing new compilers, for example, what you're just talking about.
Yeah, I think you're going to need a whole bunch of techniques to handle issues to do with concurrency and parallelism.
Yeah.
We're going to need coordination synchronization methods like which George has talked about. Sometimes you need techniques for atomicity. So you might want to use things like software transactional memories.
Yes.
Sometimes a lock is what you need, and that's
Right.
exactly what it's the right thing for that particular task. So I think we need to increase our toolbox of power tools for concurrency and use the right tools at the right level.
Perfect.
And one of the things that Satnam has done, and we have also had the intuition, is that certain things are extremely complementary of each other. So trying to use joins for locking, we actually think is a horrible idea. It's almost as error prone as just using locks.
Okay.
But using joins for coordination, which is what I showed you, is extremely powerful. So what do you do for locking and atomicity? STMs are perfect. And because we already do some capture of the delegate, you can just make the whole thing independent of all other delegates running in parallel.
Okay.
So they have this natural, I personally believe, point where I don't really care how you do correctness in terms of memory. You can use STMs, you can use locking, it doesn't matter. But it shouldn't show up anymore. And the STM guys have really been saying that. You shouldn't have to worry about that. The system should do it for you. Furthermore, here we're saying you can integrate this with coordination. So you have the shared memory thing, which you always have shared memory within some, or the illusion of shared memory within some scope. And then you use message passing for some medium to coarse grained coordination.
I think more we want to declare what we want to do rather than imperatively issue orders about what we want to do. So here we're declaring how some synchronization should occur, and the system tries to make it happen in an effective way. With STMs, you're trying to declare that some group of instructions should be atomic, and then the system decides how it should use locks or however it should implement that. So we want to raise the abstraction of concurrency constructs and programming techniques so that you declare more what you want, and then the system has the maximum flexibility to implement it correctly and as efficiently as possible.
Fantastic. This is great. So I mean, it's important to stress that this is not like the solution to the concurrency problem. I mean, with a name like Common Concurrency Runtime.
Actually, we call it coordination and concurrency runtime.
Thank you. Much better.
Yeah.
Well, that's important.
No, we think so.
This is a great beginning to
Right.
higher level abstractions
Right.
to a very complex paradigm for
And it's something you can
many
use now. It's not hand wavy. It works.
It's very practical and pragmatic.
Very
and
stable.
And it's very clever with your use of it. What you get in 2.0 with iterators, and
Yeah.
obviously the help that generics gives you.
Yeah.
But that example right there is particularly innovative.
Yeah.
So fantastic. We're gonna, we're very interested to see how this evolves.
Mhm.
And thank you for your time.
Thank you.
And we will have a bunch of information up on Channel 9 when the time comes, including links to your paper, links to the downloads. We have a wiki.
Yeah, there's a wiki already.
And you guys are going to join Channel 9 and answer questions.
Absolutely.
Right?
Okay,
And
sure.
talk to Niners about this
Absolutely.
stuff. We have a lot of developers that come to our site. So.
Well, we want to raise awareness that this exists right now and engage people, because the more people we show this stuff, the more excited they get about using it.
Now I'll tell you, at the PDC, the talks on concurrency were, at least to me, surprisingly popular. Did you guys go down and talk about
No,
this?
but we
at all?
heard about that.
Yeah, I mean they're very, very. It's a very real problem. I mean
Yeah.
that is now being addressed, and I think people are really going to like this.
So again, to stress, and I think people will get to that, is that they are excited, I believe, about writing applications that are correct, they're responsive, they do their work. Concurrency is not really a problem. It's just that, again, we're not really CPU bound today. There are certain classes of applications we are CPU bound, but a lot of this has to do, in my personal belief, with making it easy to people to coordinate. And the more cores you have, the more you might find it useful
Sure.
to coordinate.
To get actually the power out of that CPU.
Right. So concurrency is almost like the wrong thing, but because it's sexy.
This is a software engineering structuring technique. It's a way for you to structure, compose, and build up your software. In addition, if you do it right, it might give you some benefits when you have multiple cores.
Absolutely. Fantastic.
Very cool. Thank you very much.
Thank
Thank
you.
you.